Hello and welcome to our first lecture. So in this class, we're going to be talking about calculus, and we're going to do calculus from a proof-based perspective. So we need to figure out where we should start. So generally when we think about calculus, we might think about things like derivatives or integrals. And those are the two sort of main topics that we often think about in calculus. But we want to make sure we start somewhere here where we can sort of prove everything from there. So we need to sort of go backwards in time and think about, what do we need to build up these things? So in order to build up derivatives, right, we need functions that we're going to take those derivatives of. And then maybe you've seen that we define those derivatives in terms of limits. So we need the idea of a limit. Well, what are these limits and what are these functions based on, right? These are both properties that we can talk about for real numbers. So we have a function that takes in a real number and gives out a real number. When we're doing limits as one real number is approaching something, and we're looking at outputs, which are real numbers. So where we're going to start in this class is we're going to actually start with real numbers and think about how we can actually find out what real numbers are. How do we actually define what real numbers are? And it turns out we need to go back a little bit before that even. And we're going to define real numbers in terms of a set with certain properties. So in this lecture, we're going to talk about sets. That's going to be our starting point. And then you'll see later that we can define what the real numbers are as a set that satisfies certain properties. Those are called the axioms. And then we'll be able to build up and prove everything from our axioms and sort of use that as our building blocks to then talk about functions and then derivatives and integrals. And actually in this class, we're going to do integrals first after we have sets, and then we'll do derivatives later. And then we'll go back to integrals at the end and connect these two ideas using the fundamental theorem of calculus. So what we want to do first, as we said, is define what sets are. So sets, the definition of a set is a set is an unordered collection of objects. Right, so what are the sort of important things here? We have that it's unordered as a collection, right? So that's kind of sounds like a different word for a set, right? But we're just trying to say, okay, I have some stuff here. That's my objects. Those objects can be anything we want. But in our context, they're often going to be mathematical objects, and a lot of times they're going to be numbers. It doesn't matter what order we put those numbers in, and maybe there's going to be some extra properties that they satisfy that we want to add to that set. So these objects, the thing that make up the set, those objects are called elements of the set. So we have these sets, which are these collection of objects. The objects in that set are called elements of that set. And we say that these elements either belong to or are contained in the set. Okay, so then we have some notational conventions here. So for our sets, just so we can all be on the same page, whenever we talk about a set, we almost always refer to it as a capital letter. That just helps so that we can recognize, if we see a capital letter, we're probably thinking about a set. And then for the elements of that set, we usually use lowercase letters. So for example, I could say I have the set A, and I can list out its elements. We use these curly braces. So maybe its elements are the A, B, and C. So I have these curly braces, to denote the beginning and the end of my set. If I list out everything, so I've listed out the elements of the set, every single one of them, so that's called roster notation. And then I have my set, and each of these are my elements. So maybe I want to talk about the fact that B is an element of set A, or just A. So I can write that as B, and we use this kind of weird epsilon, and then A, and that means is an element of. So you'll get comfortable and sort of see this notation a lot. So we can kind of see it now as a starting point. So now we've defined sets, and we want to be able to do stuff with them. So the first important thing to know about sets is what it means for two sets to be equal. So two sets are equal if they contain the same elements. So for example, set A here has the numbers 1, 2, and 3 as its elements, and B has 1, 2, 3, and then 1 again. Listing something twice doesn't actually change it. You can't have two of the same element in your set. So I shouldn't have really listed this 1 a second time. But even if I do, it doesn't really add anything else to that set. So my set A and my set B are equal to each other because they contain exactly the same elements. Now set A and set C are not equal to each other, and set B and set C are not equal to each other, since C has 4, right? It has an element which A and B don't have. But one thing that I can notice is that all of the elements in A are also in C. C just has a little bit of extra stuff. So all elements that are in A are also in C. So that means we have a subset. So I denote that using this notation here. So this means subset. So I can say A is a subset of C. I could also say B is a subset of C, because every element in B is also in C. I could say that A is a subset of B, because every element in A is also in B. And I can say that B is a subset of A, because every element that is in B is also in A. So those are all of my subsets. This subset symbol is kind of like a less than or equal to. So I could also have the subset without the equal. So this is sort of proper subset, which means it's a subset and they're definitely not equal. So everything in A is in C, but C has more stuff. So I could say B is a proper subset of C as well, but I can't say that A is a proper subset of B because B doesn't have any more stuff than A does. One other thing we can notice here is that A and B are both subsets of each other. And that's true since A and B are equal. Since they're equal, everything that's in one is in the other, and vice versa. So this is actually going to be our first theorem. So we talked about that first theorem on the last page. Let's write it out. If any set A is a subset of a set B, and that set B is also a subset of A, then A has to equal B. Right? So we said if A equals B, that it's necessarily true by definition that A is a subset of B and B is a subset of A. But now the theorem is if A is a subset of B and B is a subset of A, then they have to be equal. So this is something that follows from the definitions, but doesn't come exactly. So we would actually have to prove this. So let's think about how we would do that. I need to try to prove that A equals B. So let's do some maybe background work here. This is where we think about what we want to show. So I want to show that A equals B. So that means I need to show A and B have the same elements. Okay, so maybe they don't have the same elements. Let's think about what that would happen. So if not, all right, so if A is not equal to B, then either A has elements that B doesn't, right? So, or in other words, there is an element in A which is not in B. So that's the first thing that could happen. Or B has an element that A doesn't. Right, so if this isn't true, right, if A and B have all of the same elements, then they're equal. And if they don't have all of the same elements, one of them has to have an element that the other one doesn't have. Okay, so what I can do is I can show that if we show that 1 and 2 are impossible, then it can't be true that A and B are not equal, so they have to be equal. Then it's impossible for A to not equal B, so A has to be equal to B. Okay, so that's just our thinking process. So now let's actually do the proof itself. Maybe we need to give ourselves a little bit more space here. Okay, so we'll say assume A has an element that B doesn't have. But since we know, right, we're trying to prove this theorem under the hypothesis, the if, that A is a subset of B and B is a subset of A. So maybe we should have started with that as our assumption. So let's throw that in. We should always assume our if. Assume A is a subset of B and B is a subset of A. Now what I'm doing is I'm sort of trying to show that it's impossible for this to not be true. So that's called a contradiction. So I'll say for sake of contradiction, kind of filling in some details here as we need them. For sake of contradiction, assume that A has an element that B doesn't. But since A is a subset of B, by definition, every element in A is also in B. I don't know what I wrote right there. Should have been a comma. So that's impossible. Similarly, since B is a subset of A, B can't have any elements that A doesn't. So A and B must have all of the same elements and thus must be equal. All right, that's what we wanted to show. We wanted to show A equals B, so we're done. I like to end the proofs with a little box here. So, right, this is our first proof in the class, so let's actually go back and sort of think about what we did here. Right, I needed to prove this statement of the form if-then. So I needed to assume the if, and then try to prove the then. Before we got started, we thought through what we needed to show and how we could go about showing that. And then we were able to use our assumptions, the things that were in the if part, to show that. And we did a contradiction. So we sort of showed it would be impossible for it to not happen, therefore it happens. It turns out this is a really important theorem and something that we're going to use throughout the course. So throughout the course, we often are going to want to show that two sets are equal. So whenever we want to do that, we're going to go back to this theorem. So we show they are subsets of each other. Because then by this theorem, they have to be equal. And it's much easier to show two things are subsets of each other, because you just pick an arbitrary element in the first, show it's in the second, pick an arbitrary element in the second, show it's in the first, and then we can get this. So these are the types of things that we would maybe do in this class, what the proofs might look like. So to finish up for this mini lecture here, I want to talk just a little bit more about notation, and we're going to talk about set builder notation. So often I want to talk about a subset of a certain set. Usually it's going to be a subset of the real numbers, but I don't want to write everything out, either because there's a lot of elements or because it's impossible because there's infinitely many elements, or I don't know exactly what the elements are yet. I just want to describe them in some way. So to do that, we use what's called set builder notation. So I could write something like the set of x, which is some sort of variable, such that, so I want to basically read this bar as such that. So set of x such that x is a real number and x is greater than 0, for example. Right, so that's the same as the set of real numbers that are strictly greater than 0. So we could use interval notation to talk about that set, 0 to infinity. We can draw a number line to talk about that set. I don't want to include 0, but I include every number bigger than that. Right, and for shorthand notation, usually we would just write this as x greater than 0. But if I really want to think about this whole set, so I want to be explicit with I'm thinking of this whole set of numbers, I would use that set builder notation. What are some other sets I could think about? Let's do some more examples here. I could say the set of x such that x is in R and x is rational. So this is my rational numbers, those that can be expressed as a ratio of two integers. We'll talk about this set a lot, so I'm going to abbreviate it with the Blackboard bold Q. So it's a Q with an extra line, just like for real numbers we use R with an extra line. I could think about the set of x. Sometimes we can put the set it's coming from on the left side of the such that bar instead of the right side. So I could say the set of x and R such that x is less than 3, or x is greater than or equal to 5, right? So that's going to be this set of real numbers less than 3, so from negative infinity to 3, or we're going to use a union symbol, and we'll talk about that more next time, the set that's bigger than 5. And let's do one more set here. So I can think about the set of x in R such that x squared is less than 0. So think for a second and see if you can come up with any elements that are in this set, right? We can't be thinking about imaginary numbers, right? I can't think about the square root of -1 because I said I'm only thinking about real numbers. And something that we know about real numbers is that when you square them, they're always positive. So this set doesn't actually have any elements in it. So you can write it with the braces with nothing in between. But generally we denote this with a 0 with a line through it, and it's called the empty set. and that's the set that contains no elements. Let's spell empty correctly. So whenever we talk about sets that have no elements in them, we always call that the empty set. And it's denoted with this 0 with a line through it. That's the most common denotation. Okay, so then in the next activity, you'll work through talking about what else you can do with sets. We'll talk about unions and intersections and complements, and some sort of strange properties that we can come up with for sets. And then remember the point is that we want to be able to build our real numbers out of this idea of sets. So that's sort of where we're going next.